Hello students, welcome to the video module on quantum theory of paramagnetism. This is a part of condensed matter physics for MSc semester 2. This is the complete module on magnetic properties of solids, and the first topic in that is quantum theory of paramagnetism. And here are some reference books for preparing this module. So now come to the magnetic materials. Materials are classified based on their magnetic properties like diamagnetic materials, paramagnetic materials, ferromagnetic materials, antiferromagnetic materials, and ferrimagnetic materials. So before going to explain these materials, you just look into some of the terms related to magnet. These terms all you learned in your lower classes: magnetic susceptibility, magnetization, intensity of magnetization, magnetic flux density, magnetic field intensity H, permeability, etc. These are some terms related to magnet or magnetism. Now, come to the various types of magnetic materials. A small description, because we have to we need a detailed description about the quantum theory of paramagnetism. That is the aim of this presentation. So, before going to that, we are having a small discussion about the different types of materials. The first one is diamagnetic materials. What are diamagnetic materials? They are materials with the atom possesses no permanent magnetic dipole moment. So they are materials with no dipole moment to the atom. So we know that what is actually the reason for for a material to become magnet. We know that an atom consists of a nucleus. Surrounding that, there is an electron revolving. So the revolving electron or the moving electron, it is equal to current. And we know that current can produce magnetic field. So this moving electron is responsible for magnetic properties. Electron has got two movements. One is the revolution, the orbital motion around the nucleus, and another one is its own spinning about its own axis. So due to this movement of electron, they produces a magnetic dipole moment. What is a dipole? What is a magnetic dipole? A magnetic dipole has got two poles, one north pole and south pole. So the familiar example is a larger one, that is a bar magnet. So just think that in a microscopic scale, an atom that also possesses a similar properties. It has got north pole and south pole. But in the case of a diamagnetic materials, the atom does not possess a permanent dipole moment of its own. Because of the various different types of orientation of electrons, no net magnetic dipole moment is seen in the case of diamagnetic materials. Come to the next type of magnetic materials. They are paramagnetic materials. In this, each atom possesses a small dipole moment of their own. But when you consider the material as a whole, if the material consists of large number of atoms, their dipole moments will be oriented in various directions. So the total dipole moment will be zero. But not like the case of a diamagnet. In the case of diamagnet, the atom itself possesses no dipole moment. Here the atom possesses dipole moment, but the material does not possess dipole moment because of their random orientation. And the other one is ferromagnetic material. Here also the atom possesses their own dipole moment. But the thing is that in the case of ferromagnetic materials, the similar dipole moments, similar direction dipole moments group to form what is called a domain, called ferromagnetic domains. So similar dipoles will be in a same direction. They aligned in the same, I mean, in a small groups called ferromagnetic domains. But in the presence of external magnetic field, all these align in the same direction and to form a strong magnet. Such materials are called ferromagnetic materials. And if these materials align alternatively to one direction, opposite directions, they are called ferrimagnets. Okay. Now come to the quantum theory of paramagnetism. So in this video module, we are discussing about quantum theory of paramagnetism. So what is the what is we learned what is meant by a paramagnetic material? In a paramagnetic material, the atom possesses their own dipole moment. And what is the reason for an atom to show magnetic property? Because atom consists of electron. Electrons are revolving around the nucleus. Also at the same time, the electrons are spinning about their own axis. So there are two dipole moments. One is the orbital dipole moment and another is a spin dipole moment. And these two together form the total magnetic dipole moment J. So that gives the magnetic properties to this material. And according to classical theory, any orientation of these magnetic dipole moments are possible. But in actual practice, it is not like that. The quantum theory allows only some specific directions which called quantized. The magnetic, according to the quantum theory, the magnetic dipole moments are quantized. They possess only specific magnetic dipole moment directions. And the paramagnetic susceptibility, the paramagnetic property of a material depends on temperature. As the temperature increases, the paramagnetic susceptibility decreases. And the law governing this, or the law that showing this property, is called Curie law. It says chi is equal to C over T. Chi is the susceptibility of the material, T is the temperature, and C is the Curie constant. So we have to derive this expression using in this quantum theory of paramagnetism. Let us see in detail about quantum theory of paramagnetism. So now we know that an atom possesses magnetic dipole moment. When an atom behaves as a magnetic dipole, what is a dipole? A magnetic dipole is having two poles, one north pole and a south pole. So just like a bar magnet. So each atom possesses two poles, one north pole and south pole. And what is the reason for this? The reason is the movement of electrons around the atom. One is the revolution of electrons or orbital motion of electrons, and the other one is the spin motion of electrons. So due to that, the atom possesses a dipole moment mu equal to minus g mu b j, where g the Landius g factor. So if this type of an atomic dipole is kept in an external magnetic field of magnetic intensity B, then the potential energy is given by the well-known expression potential energy of a magnetic dipole in an external field B is U equal to minus mu dot B. But you can replace mu with mu is minus G mu B times B and J, then B cos theta. And this can be rearranged to, or the minus and minus it become plus G times mu B times B J cos theta. So an atom of magnetic dipole moment mu is kept in an external field B. The potential energy is given by G mu B times B J cos theta. Now J, the total magnetic moment, the sum of orbital motion and spin motion is given by J, and the projection of J along the direction of external field is J cos theta. We can represent it by Mj, the magnetic quantum number. Therefore, this expression for potential energy can be now written as G times mu B times B, and instead of J cos theta, we can write it as Mj. This is U. So, an atom of magnetic dipole moment mu is kept in an external field B. The potential energy is given by G mu B times B J cos theta. Now, J, the total magnetic moment, the sum of orbital motion and spin motion is given by J, and the projection of J along the direction of external field is J cos theta. We can represent it by Mj, the magnetic quantum number. Therefore, this expression for potential energy can be now written as G times mu B times B. And instead of J cos theta, we can write it as Mj. This is U. Potential energy U equal to minus G mu B Mj B, where this Mj, the magnetic quantum number, it has values from minus J to plus J. It has values from minus J to plus J. So if J has a value 2, then Mj has value 5, or the total number of values for Mj are 2J plus 1 values will be there, because it is from minus J to 0, then 0 to plus J. Therefore, totally there will be J value and J value and 0 value. So, totally 2J plus 1 values will be there for Mj. As an example, for the 1s electron, take the example of 1s electron. We know it has L value is equal to 0 and spin value is half. So, J value will be L plus S. So, what is that? 0 plus half, that will be half. So, what will be the Mj values? The Mj values will be minus L to plus L. So, minus half, comma, plus 1, that will be minus 1 minus half plus 1 will be plus half. So, the two values of Mj are minus half and plus half. And also for G equal to 2, what are the possible values of potential energy? We can write for one for Mj equal to minus half and G equal to 2. Another one Mj equal to plus half and G equal to 2. So what will be the values of U? U will be minus half. Mj is minus half. Therefore, G is 2. 2 and minus half cancel. Minus and minus plus. So this will be mu B times B. And for the other one, it will be minus mu B times B. These are the potential energies in the presence of an external field. So normally the energy, if there is no field present, the potential energy is given by a single value. What is that? But due to the presence of the external field, the potential energy is split to two. One is U corresponds to U equal to mu B times B, and another one is U corresponds to minus mu B times B. So now that in presence of an external field, the atomic energy levels. So earlier it was a single level when there was no external field applied, that was B equal to 0, there is only one energy level. But in the presence of an external field, the energy levels split into U equal to mu B times B and U equal to minus mu B times B. Now let us see that there are N1 particles having energy equal to minus mu B times B and N2 number of particles, N2 number of atoms having energy equal to plus mu B times B. So N1 is the number of atoms having energy minus mu B times B and N2 is the number of particles, number of atoms having energy plus mu B times B. Now, so that the total number of particles N equal to N1 plus N2. And according to Maxwell-Boltzmann distribution function, N1 is proportional to e raised to minus U, the energy, divided by K T. But what is U? We can substitute for that. That is proportional to e raised to, instead of minus, instead of U, we can substitute. What is the value of U? N1 is having minus mu B times B. So already there is a minus. So minus mu B times B divided by KT. Or we can say N1 equal to, proportionality can be eliminated with the constant N0 e raised to mu B times B divided by KT. Similarly, N2 is given by N0 e raised to minus mu B times B divided by KT. Now, let us take this mu B times B divided by KT as X. Then the equation for N1 will be N0 e raised to X. And N2 will be N0 e raised to minus X. We have calculated the population in upper and lower energy level. So in lower energy level, N1 is equal to N0 e to the power X. And in the upper energy level, N2 is equal to N0 e to the power minus X. And the total number is given by N equal to N1 plus N2. That will be N0 e to the power X plus N0 e to the power minus X. So we can take the N0 as common outside. Now, the fractional population in lower state, fractional population in lower state is N1 divided by total population, N1 divided by N. That is, it will be actually N0 e to the power X divided by total is N0 e to the power X plus e to the power minus X. We can cancel N0. So this will be e to the power X divided by e to the power X plus e to the power minus X. And similarly, the fractional population in higher state, that will be N2 divided by N1 equal to e to the power minus X divided by e to the power X plus e to the power minus X. So we have the fractional population in the lower and upper state. So let us do the values of this fractional population, or we draw the plot between fractional population on y-axis and the x value. What is x actually? X is mu b divided by kbt. So a graph between fractional population and x. So for this, let us start with x equal to 0. So when x equal to 0, the fractional population in the lower state, that is n1 divided by n2, that will be e to the power 0 divided by e to the power 0 plus e to the power 0. That is 1 divided by 1 plus 1. That is zero point 0.5. Similarly, the fractional population in the upper level, n2 divided by n, n2 by n, that is equal to, again it is e to the power 0 divided by e to the power 0 plus e to the power 0, that is 1 divided by 1 plus 1, that is zero point 0.5. So at x equal to 0, both the upper and lower energy levels has got the same number of particles, the same fractional population, zero point 0.5. But as the x value increases, we can see that the lower level has got e to the power plus x. Therefore, as the x value increases, the lower state population, fractional population, the lower state increases. At the same time, fractional population, the higher state, it is e to the power minus x. So as x increases, the fractional population in the upper state decreases, and the graph, the plot will be like this, as shown in the diagram. Now we have the fractional population n1 by n is e to the power x divided by e to the power x plus e to the power minus x, and n2 divided by n1 is e to the power minus x divided by e to the power x plus e to the power minus x. Now let this be the direction of external magnetic field applied, B. Then in the lower state, the mj values, you can see that in the lower state mj values are minus j. So in the lower state mj values are minus half. So you have to draw that opposite to the direction of the applied field, that is mj values are in this direction. But the magnetic dipole moment will be in the direction same as that of the applied field. At the same time, in the upper energy level, the mj values are plus half. So you have to draw the mj like this. At the same time, the magnetic dipole moment will be opposite. Mu will be opposite. Okay. So now, what will be the net magnetization? The net magnetization is capital M equal to N1 mu minus N2 mu. You can see there are N1 particles with a mu dipole moment in the upward direction, and there are N2 particles with a mu dipole in the downward direction. Now you can take the mu out. This will be N1 minus N2. What I'm going to do is I'm going to multiply with the total population n and divide with the total population n. So you will get mu n times n1 divided by n minus n2 divided by n. This will be mu n. What is n1 by n? n1 by n is e to the power x divided by e to the power x plus e to the power minus x minus n2 by n1, that is e to the power minus x divided by e to the power x plus e to the power minus x. Taking LCM, magnetization M is equal to mu n times e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. This is actually the expression for hyperbolic tan. So you can write it as mu n tan hx. So magnetization is given by mu n tan hx. So we have the total magnetization M that is equal to n times n is the total population, mu the magnetic dipole moment, tan hyperbolic tan of x. But what is x? X is mu b times b divided by k b t. Now, if this x value is very much less than 1, then tan hyperbolic tan of x can be approximated to x. Therefore, the above expression we can write the magnetization M as n times mu times x. But we know that is mu. Mu is g mu b the Bohr magneton times j the total angular momentum. I mean the total magnetic moment quantum number j, orbital plus spin. But for 1s electrons, for 1s electrons, we know that g value is 2 and j value is half. So if we use this value, then what will be the mu value? Mu will be 2 times mu b times 1 by 2. So 2 and 1 by 2 cancel. You will get only mu b. So the magnetic dipole moment is equal to the Bohr magneton. Mu equal to mu b. So how can we write now? That is n times mu b times x. What is x? That is also mu b times b divided by kb t. This can be written as n mu b square times b divided by kbt. But what is b? B equal to mu 0 times h. Mu 0 is the permeability of free space. So we can substitute that here. M equal to n mu b square. This mu b is the dipole moment, magnetic dipole moment, or this mu b is the Bohr magneton. And in this case, for 1s electron, we know that the Bohr magneton and the magnetic dipole are same. Okay, and instead of b, you can substitute a mu 0 times h divided by k b times t. Now, h can be taken as m divided by h. This is actually known as the magnetic susceptibility chi, that is equal to n mu b square mu 0, all these are constants, kb times t. So n is constant, mu b is constant, mu 0 is constant, kb is constant. So we can say chi is proportional to 1 divided by t. This is what we already know, that the Curie law, mu proportional to 1 by t. We have the expression for magnetization m equal to n mu tan hyperbolic x, and the susceptibility chi equal to n mu b the Bohr magneton square, mu 0 the permeability divided by kb t. This actually we derived for 1s electrons, which has an mj value of plus or minus half and with a j value of half. But for in general case, for any type of any electron system, we know that mj has got 2j plus 1 values, 2j plus 1 energy levels. So instead of tan hyperbolic tan x, we have to use another term or another function. So the term will be like M, the magnetization M will be N mu. Instead of the hyperbolic tan x, we have to write it is a new term, that is Bjx. This is for any electron energy level 2J, for any electron system. The magnetization is given by N mu Bjx, where this Bj is called the Brillouin function. And on a simplified value of this Bj can be written as I'm just skipping the in between steps. The simplified value of Bj of x can be written as x times j plus 1 divided by 3j. And what is the x value? X is mu b times b divided by kbt. So using this value of Bj, the Brillouin function, the magnetization M can be written as N mu. Instead of Bj, you can write x j plus 1 divided by 3j. Now substituting for x, this equation becomes N mu j plus 1 divided by 3j. Now there is an x. Instead of x, you can write mu b times b divided by kbt. So magnetization M equal to N mu j plus 1 mu b times b divided by 3j kbt. Now we know that the value of mu is approximately equal to the mu b. We can write it as M equal to N mu square j plus 1 b divided by 3j kbt. But what is mu? Mu is, magnitude wise mu is g mu b j. If you are writing in vector form, then it will be the negative. Okay. Magnitude is mu is equal to g mu b times j. So we can write that mu here, it will be n. So it's mu square. So that will be g square mu b square j square. Then again there is a j plus 1. Then there is a b. B can be, okay, B can be written as mu 0 times h whole divided by this. B is replaced by mu 0 h. 3j kbt. One of the j cancel from this. So it will be m equal to n there is n, then mu b square, then there is j into j plus 1, there is a g square also, this is mu b square divided by 3 kbt. So this g square into j plus 1, I'm going to replace it with n. There is mu 0 h also there, we missed it. Okay, this can be written as n mu 0 h mu b square p square divided by 3 kbt, where p square is g square j into j plus 1, or p equal to g into root of j into j plus 1. It is the effective number of Bohr magnetons. P is termed as effective number of Bohr magnetons. So we got the expression for M equal to N mu 0 H mu b square p square divided by 3 kbt. We have magnetization M equal to N mu 0 mu b square p square divided by 3 kbt times h. We take the h to the left side, it will be m divided by h. But what is m divided by h? This is susceptibility chi is equal to n mu 0, the permeability, mu b, the Bohr magneton square, p square, the effective number of Bohr magnetons, divided by 3 kbt. So these all terms are constants, and we can write chi is equal to a constant c times, or c divided by t, where c equal to n mu 0 mu b square p square divided by 3 kb. This is the Curie constant, and we got chi equal to c by t, the Curie law.